Hello, my name is Joel Park. Today I'm going to present about active helps pre-trained models learn the intended task. Models can fail in unpredictable ways during deployment due to task ambiguity. Task ambiguity is a situation where the defined task may differ from the intended task based solely on the characteristics of the data. In this figure, there is a red square and blue circle. It is ambiguity. What is important property, color, or shape? Using active learning, we can resolve this task ambiguity. Active learning upsamples new data, blue square, making this task clear. So what is active learning? Active learning aims to improve model performance by selectively querying the most informative data points for labeling. Conventional machine learning just labeled or unlabeled data, but it is difficult and demands a lot of effort. But using active learning, we can automatically and adaptively select most informative data for labeling. So it reduces human effort. So in this paper, active learning is used to solve the task ambiguity automatically. This is procedure of active learning. And first, active learning fine-tunes model M on a small set of training data S until convergence. And then select points X from a larger unlabeled pool P that are deemed most informative according to acquisition function A and obtain the corresponding labels Y. Repeat it until some budget K of data points is exhausted. This newly labeled batch B is then added to the existing data S. The original model M is retrained on S. This process is repeated for a fixed number of acquisition steps. This is acquisition function. In this paper, the classic uncertain sampling is used. Uncertainty sampling is a method for selecting based on the model's uncertainty regarding the data. It consists least confidence margin sampling and entropy. Least confidence is used mainly in this paper, and it selects data points where the model has the lowest maximum class probability. And margin sampling selects data points based on the smallest margin between the two most probable classes. And entropy selects data points based on the highest entropy, which measures the uncertainty of the model. And this is example of uncertainty sampling method. So if you are curious about the method, please refer it. And the main contribution is the introduction of pre-trained model in active learning. Pre-trained models trained with active learning are used to select examples that resolve task ambiguity. The effectiveness of using pre-trained models in active learning is validated through various experiments. This is dataset. It is divided two categories. One is distinguishing causal from spurious features. The other is measuring robustness to distribution shift. Each part uses two kinds of dataset. So first is Waller-Verse. It is to classify whether a bird in a land or rural background is a land bird or rural bird. Extra causal picture is Waller type, but spurious picture is image background. And the train and test distribution differ. In train dataset, 95% is land birds on land background and 95% waterverse on water background. In test dataset, 50% is landverse on land background and waterverse on water background. And second is 3%. It is to classify whether there is a person in a given image or not. So actual casual picture is person, and spurious picture is terrier building. In trained dataset, 90% people with a building and people without a tree. In test dataset, just 50% each. Third is iWorldCam 2020 WISE. Data collected from cameras installed in the wild for the classification of animal species. The dataset is imbalanced with the majority of images not containing animals, and the distribution of animal species and camera locations in the train set and test set differs. You can see the figure how the dataset consists. And last is Amazon WISE. This is the only text data. Predict the number of stars associated with the text of a given Amazon review. Different reviews in the training set versus the test set. Consider model performance stratified by different product types, which highlights minority subgroups whose categorization is not visible to the model. This is model and acquisition baseline. VIT model is used for vision data, and Robert Tallers is used for text data. And random acquisition baseline, which is aimed not to use active learning, is used to compare performance. This is the result of accuracy per acquisition. You can see that using uncertainty sampling, better performance is achieved with less data compared to random sampling. You can see that the orange color means uncertainty. It shows better performance. And this is results comparing other active learning methods introduced in method part. Using uncertainty sampling, better performance is achieved with less data compared to random sampling, especially in other classes. And this shows that active learning with pre-trained models selects examples that resolves task ambiguity. Pre-trained models identify and upsample ambiguous examples where spurious picture and casual pictures do not match in this case. Similar to waterverse and 3%, Amazon dataset also shows that pre-trained models enable data collection focused on less common features, even in the presence of domain shift, like this. Pre-training is the key ingredient in these experiments. When we show these experiment results, we can know that using pre-trained models in active learning improves performance. In situations with task ambiguity or data imbalance, using non-pre-trained models can result in uncertainty sampling performing worse than random sampling. And this is a part of pre-training on acquisition. Using pre-trained model A, B, C, oversample ambiguous examples with mismatched backgrounds. Using non-pre-trained models D, only oversample images with a water background. Pre-training is a better picture space for active learning. To quantitatively evaluate the linear separability of a wide range of pictures in the picture space of pre-trained models, linear classifiers are trained on the second to last layer of the VIT models. The research shows that the classifier in the pre-trained models exhibit much greater linear separability. This is impact of task ambiguity of active learning. As the proportion of mismatched examples increases, the gain from active learning gradually increases. This is Superior case. It tested the different data set from the distribution of the pre-trained model. When training on data sets that are significantly different from the distribution of the pre-trained model, active learning performed similarly or worse than random sampling. So this is conclusion. Pre-trained models can resolve task ambiguity through active learning. And in situation of task ambiguity, not using pre-trained models can lead to sampling being performed in the wrong direction. So thank you for listening my presentation.
I will introduce about Divide and Not Forget, Ensemble of Selectively Trained Experts in Continual Learning, which was presented at ICLL in 2024. Continual learning, also known as lifelong learning, refers to the ability of a model to learn continuously by accommodating new information while retaining previously learned knowledge. This approach is crucial for developing models that can adapt to new tasks and environments without forgetting what they have already learned. Continual learning is divided into three main categories: task incremental learning, domain incremental learning, and class incremental learning. In task incremental learning, the model sequentially learns to solve a number of distinct tasks. And in domain incremental learning, the model learns to solve the same problem in different domains. Lastly, class incremental learning involves discriminating between incrementally observed classes within a single unified task. And the paper to be introduced today focuses on class incremental learning. Class incremental learning is a specific type of continual learning. In this context, for each task T in a set of tasks, we have a training set DT. Here, X, Y, and CT represent an input sample, its corresponding label, and the set of classes for task T. Importantly, CT are disjoint across different tasks. The goal of a class incremental learning is to learn a function f. This function should map input samples to the set of all classes observed up to and including task T. Simply put, class incremental learning has two main goals. The first is preventing catastrophic forgetting. Catastrophic forgetting occurs when a model forgets previously acquired knowledge upon learning new information. This happens because the system needs to adjust parameters to accommodate new classes. Preventing catastrophic forgetting is crucial because losing previously learned knowledge undermines the whole purpose of continual learning. The second goal is training the model with new knowledge. This involves updating the model to incorporate new classes. This is also vital to ensure that the model can effectively integrate new classes. As a result, class incremental learning aims to learn new knowledge while preventing catastrophic forgetting. For class incremental learning, several approaches are proposed. Regularization-based methods add regularization terms to prevent drastic weight changes, making them resource efficient but less effective and sensitive to hyperparameters. Replay-based methods store and replay old data during training, requiring significant storage. Architecture-based methods adapt and expand the model structure by adding new components to accommodate new tasks, which is effective but requires large memory. Ensemble-based methods leverage multiple models or experts, each specializing in different tasks to collectively address class incremental learning. A key approach within this category is the mixture of expert method, where a gating mechanism selects the appropriate expert for each input, ensuring efficient learning and robust performance. This approach has gained significant attention in recent research due to its flexibility and effectiveness in preventing catastrophic forgetting. However, the experts are usually trained all at once using whole task data, which makes them all prone to forgetting and increasing computational burden. The paper I will present addresses issues within the mixture of expert approach. The previously introduced methodology for addressing catastrophic forgetting face the following challenges. They often have high plasticity, enhancing adaptation to new tasks but risking the loss of previous knowledge. Ensuring stability can limit flexibility since it involves preserving parameters from older tasks. Additionally, many approaches are computationally demanding and require substantial memory. Hence, it's essential to develop methods that balance plasticity, stability, and computational efficiency to effectively address these issues. To address these limitations, the author introduces a novel approach named SEED, Selection of Experts for Ensemble Diversification. SEED selects only one, the most optimal expert for a considered task, and uses data from this task to fine-tune only this expert. Consequently, SEED increases diversity and heterogeneity within the expert while maintaining the high stability of this ensemble method. The core idea of this approach is to directly diversify experts by training them on different tasks and combining their knowledge during the inference. Each expert contains two components, a feature extractor that generates the unique latent space, and a set of Gaussian distributions. The overlap of class distributions varies across different experts due to disparities in expert embeddings. SEED takes advantage of this diversity, considering in both during training and inference. Specifically, the following figure shows an example of SEED training process for 2 experts, 3 tasks, and 2 classes per task. When the third task appears with novel classes, it analyzes distribution of C3 classes in latent spaces of all experts. Then it chooses the expert where those distributions overlap least. Finally, it fine-tunes this expert to increase the separability of new classes further and move to the next task. First, the experiment utilized 3 datasets. Each dataset was tested under the following 3 different scenarios. In equal split scenario, each test contains an equal number of classes. SEED achieves spurious results compared to other methods with a large margin. In larger first task scenario, the first task contains a larger number of classes than the subsequent tasks. The difference between SEED and other methods is noticeably smaller in this scenario than in the equal split scenario. This fact proves that SEED works better in scenarios where a strong feature extractor must be trained from scratch or where there is a domain shift between tasks. Lastly, in task incremental scenario, the task ID is known during inference and tasks are equally split in terms of classes. Despite being designed for exemplar-free class incremental learning, SEED achieves superior performance even in task incremental settings with limited parameters. A decrease in the number of parameters means an increase in the number of shared layers. This increase in the number of shared layers can reduce the required parameters, but it may negatively affect the accuracy of task-specific performance. Compared to other vanilla ensemble approaches, SEED demonstrated the highest performance, proving that the improved performance of the method is due to more than just forming an ensemble classifiers. Additionally, the picture below left represents relative accuracy, with black squares indicating the experts chosen to be fine-tuned for the given task. It can be observed that these experts are specialized for the fine-tuned tasks, demonstrating that each expert uniquely contributes to SEED's ensemble. Finally, the right-hand figure shows that the KL-MAX method, which selects experts with minimal overlap, outperforms other selection methods such as random robin and K-mean. To assess the influence of the regularization on overall method performance, forgetting and intransigence are measured. Forgetting and intransigence was the proposed evaluation matrix in 2080 to better understand the behavior and performance of an incremental learning algorithm. SEED achieves much better results than other methods while remaining less intransigent and more stable. By adjusting the alpha trade-off parameter of seed, it shows that its stability can be controlled for any number of experts. As a result, SEED addresses the challenge of catastrophic forgetting by updating only the parameters of a single expert model. This approach helps preserve the learned representations of other experts. By training only one expert at a time, SEED achieves two key benefits. First, it enhances the diversity of class representations among experts, effectively balancing plasticity and stability. Second, it reduces the computational cost during the learning process. In summary, SEED's innovative approach significantly improves the efficiency and effectiveness of continuing learning systems. Thank you for listening.